All right, welcome back. Hope you all had a good weekend. All right, here we go. Okay. So what happened here? All right. I thought I had the slides up already. Okay, so I've been going over some miscellaneous but interesting topics that have to do with compilers. You may or may not need to use any of these in your compiler projects, but these are the sorts of issues that professional compiler writers have to deal with. And so even though for this class, you may not need to, at least you'll know about these issues, okay? So today, what I want to cover is runtime memory management. And I know we have discussed this topic before when we were creating the Pascal interpreter, okay? Remember, we had the runtime stack and these stack frames that were pushed onto the runtime stack every time we called a function. And the stack frame, of course, contained the current runtime values of all the local parameters and variables of that function. And then when we returned from that function, we popped off the stack frame. And to help the runtime access the values of non-local variables, we had the runtime display, which always pointed to the topmost stack frame at a particular nesting level. So that was what we did. Boy, it seems like a long time ago, forever ago, when we were building the interpreter for Pascal. Okay. Any questions at all? Before I move on, I guess I should have asked this earlier. Any problems people are running into with Antler because you're finishing the last assignment and you're busy working, I hope, on your projects. I know a few of you have come to me and we've managed to solve a few Antler issues, namely making sure you're picking up all the header files and picking up the libraries and so forth. It's just a matter of making sure that you have those all in the right places in your file system. And then if you're using Antler, if you're using Eclipse or Sea Lion, you just have to point your IDEs to the right directories for it to find all the header files and all the libraries during linking. And hopefully you're all able to use Antler. All right. Any questions at all about anything before I dive into today's topic? Okay. All right. So what we're going to talk about today is runtime memory management. And as I said, you've seen how the interpreter manages runtime memory. Okay. Now we did talk a little bit about dynamically allocated data. I said it goes into an area of memory known as the heap. And if you remember our very simplified diagram of the Java virtual machine, here's the runtime stack, here are the stack frames, and then here's the heap. And so whenever we create an object, okay, object's actually created out in the heap. Okay? And then in the stack frame, of course, there was the local variables array. And if a variable value was an object, then of course, what was really happening is that slot in the local variables array will have a pointer to one of these objects. Okay? Mostly that's hidden from you. You just have to know to create the object, and then the JVM would put it out in the heap. Okay. Now, if we kind of step back and from this diagram and look at the whole process of of your program that's running, you can think of your memory. Okay, well, here's another way of thinking about how your memory is partitioned. Okay, so here, if this is your memory partition, okay, so you're running your program, and the operating system has allocated memory for you. Okay, this is sounding like my operating systems class, but okay, so you have memory allocated for you. At one end of your memory will be what's all the static stuff. Okay, so all the executable code. Okay, the code itself presumably doesn't change, and any statically allocated data. So these could be like constants and whatnot. Okay, that's at one end of your memory. Okay, then you have the runtime stack. Okay, and here's the top of the stack. Okay, and then you have the heap. So the heap is here. Okay, and as you know, the stack can grow up and down, and the heap can grow if as we're allocating more and more objects, the heap can grow in size. Okay, now in between the stack and the heap is the free memory. Okay, now as you can imagine, if you're doing something, say with recursion, and the stack runtime stack is growing and growing and growing, and meanwhile you're allocating more and more objects, so the heap is growing and growing, you can run out of free memory. Okay, and a fancy term for that is a heap stack collision, because the heap and the stack are going to crash into each other, which happens when you run out of free memory. Okay, and that's when you get the out of memory error. Okay? Now the way I've drawn this may not be exactly the way. Let's say you have a process running in a Linux server. Okay, and even on a Mac. This is pretty close to the way a process really looks at memory, but I think on Linux, the heap and the stack are reversed. I mean, the heap will be here, okay, and of course, the top of the heap will be this line here, and the heap will grow this, I'm sorry, the runtime stack will be in here, and this would be the top of the stack, and the stack will grow this way. And here, where I have runtime stack, is the heap, and the heap will grow upwards, and then you still have the free memory in between. Okay, but as far as we're concerned, we have the heap, we have the stack, and they both grow towards each other, and you hope that they don't collide. Okay. All right, so this is here is this is the fanciful diagram of what it looks like, but in reality, it looks more like this. Okay, so you just get a region of memory that's been allocated to your program, and this is how that memory is partitioned. Okay, all right, so. Okay, now how is this heap managed? Okay, the objects that we're creating out here in the heap, how is that managed? Okay, now different languages have different ways of managing the heap. Okay, C and C++, whenever you want to dynamically create something out in the heap, you call it new or malloc, right? And then when you're done with that object that you created up in the heap, presumably you'll remember to call delete or free on it to free up that memory. Okay, so languages like Pascal, C, and C++, you're pretty much responsible for managing the heap. If you need something out there, you're going to create it, and when you're done with that object, it's your responsibility to deallocate it. Okay, otherwise, you're going to litter the heap with all these objects that you no longer need and quite possibly can no longer access. And so you have to be sure to deallocate anything that you allocate dynamically. Okay, so you're in charge of the heap. Okay, now in Java, Java is one of those languages that has automatic garbage collection. So just like in C or C++, in a Java program, whenever you need a new object, you call new. okay, and then there's the object, okay. But later on, when that object is no longer used, it's automatically deallocated for you, okay. That's called garbage collection. So objects that are no longer accessible, okay. That's how the Java runtime decides that an object is no longer used. If you can no longer access it, like you've lost the last pointer to that object, then that object becomes garbage, okay? And then the garbage collector notices that and deallocates it for you. That's known as automatic garbage collection, okay? So Java does that, but other languages do not, okay? Now, I will point out that the latest versions of C++ has what are known as smart pointers. And smart pointers, not quite like garbage collection, automatic garbage collection, but pretty close. And with smart pointers, when objects go out of scope, they are automatically deleted. Okay, so it's almost like garbage collection, but not quite. Okay, but then you do have to use what are known as smart pointers. And in my 135 class, I will cover smart pointers. Okay. All right, so heap management. Okay, that is something that if you're going to write a compiler for a language, you have to consider this. Okay. Now, heap management then requires keeping track of all the allocated blocks of memory. So when you create an object in the heap, you've allocated some blocks of memory. Now, there's usually some fixed size block like 4K or the block size can vary, but usually it's a fixed size, and when you allocate an object, you'll get enough blocks for that object, okay? So you have to keep track of all the allocated blocks in the heap and all the free blocks, okay? The blocks in the heap that are not currently allocated, okay? So the free blocks are called holes, and generally they're created when you have an object and then you deallocate the object, then what's left behind is known as a hole, okay? It's basically blocks that are now available for some other object to occupy, okay? All right, so who's keeping track of all this? Well, hopefully it's not your program. The runtime system is keeping track of it. So if it's you're running a C++ program or a Java program at runtime, there'll be library functions that are automatically, well, actually it's a separate process. So your process is running and your program is allocating objects in the heap and deallocating them and so forth. Well, there's, when you start up your program, C++ has a separate process that's keeping an eye on the heap and managing it by keeping track of all the allocated blocks and all the free blocks. Okay, so your program doesn't have to worry about it, but when your program is running, okay, somebody is keeping track of what you have out in the heap. Okay. All right, so when your program says, hey, I'm going to create a new object, I want to allocate a new object, okay, where in the heap should that object go? Okay, well, again, the heap manager is going to figure that out, okay? Now, when I say you, I really mean the heap manager, okay? So this object can be allocated at the end of the heap, okay? So that means the heap will keep growing, right? Okay, so if you go back to this diagram, all right, we're allocating objects, and we always allocate at the end of the heap. So that means the heap limit has to keep moving forward. Okay, so that's one way. Okay, the other way is to remember the heap will have holes in it because you may have deallocated objects earlier. So now if you want to allocate a new object, try to put it in a hole so that you're reusing some memory, and then you don't have to make the heap any bigger. Okay, so there are various schemes for how to allocate dynamic objects in a heap. Okay. Now, if you're going to try to put objects in holes, right? So you know, after your program is run for a while, your memory is going to kind of look like Swiss cheese, right? You're going to have all these allocated blocks of memory, and then in between the allocated blocks are going to be these holes, and so so now if you decide, okay, if the heap manager says, hey, I'm going to try to not grow the heap unless necessary. So whenever there's a request to allocate blocks for a new object, then it's going to look for a hole to put that object in. Okay, and so finding that hole, there are several algorithms, and if you're taking 142 from me, you've already explored these algorithms. The heap manager can just do a scan of the heap from one end to the other, and you know, so you tell the heap manager, hey, I want to allocate an object, and it's going to take 10 blocks. Okay, and so the heap manager will then scan the heap from beginning to end, looking for the first hole that's at least 10 blocks in size. And if it as soon as it finds that hole, it's going to put your object in there. Okay. So that's one algorithm, just scan from start to beginning at the beginning of the heap, and as soon as it finds a hole big enough, that's where your object goes. Okay. Now the other algorithm says, well, let's see if we can do better. Instead of just sticking the object in the first hole that's big enough, let's look for the smallest possible hole that the object will fit in. Okay, so if your object's going to need 10 blocks, then let's look for the hole that is the smallest hole that is at least 10 blocks, and then we'll put the object there. Okay, the idea, thinking is that you better utilize memory that way instead of just sticking the object in the first hole that's big enough. Okay, there's yet another algorithm that says, well, we'll just randomly pick a hole. And well, randomly pick a hole that is 10 blocks or bigger. Okay, so I mean, you would randomly pick a hole that's big enough. But of all the holes in the heap that's at least 10 blocks in size, we'll just randomly pick one and then stick the new object in that hole. Okay? So there are even a few more algorithms, but you know, these are some of the algorithms that the heap manager can use when you ask it to allocate memory for a new object. Okay? So actually, let me show you a little demo here. This was actually an assignment in my operating systems class where we simulated. We did a live animation of memory allocation. Okay, and so let me fire that up, and it may be amusing for you to watch this. Okay, so here, okay, this is going to be a picture of memory as soon as I get going, and I'm going to fire up 3 programs that are simultaneously asking for the memory manager, okay, which presumably is managing the heap. Let's fire up 3 separate programs named A, B, and C that will be making requests to allocate blocks. And after a program has allocated a block, later on it will deallocate that block, and so you're going to see holes also being created. Okay, all right. So let's see this. Okay, so this is the memory manager. Okay, and let me open up A, B, and C. Okay, okay. There is program A, and here's program C, and here's program B. Whoops, get this right. Okay, okay. So here's program A. It's going to be making its memory request. Program B and program C, and they're all going to be doing that. Different sizes of objects, and after it's gotten an allocation for an object, later on it will then go back and delete that object in order to create a whole. Okay, so I'm going to start up requester A, and here I'm going to start up. Now this is set up to do the first fit. Okay, so again, the way this works is that the memory manager scans the heap from starting at the beginning, looking for the first hole that's big enough to fit the object, and then it puts the object there. Okay, so here we go. Okay, here's, remember, I can see these A's are objects that are being requested by this guy, and here's B. Now you can see B requests being filled in there, and here is C requests. Okay, and these slashes are holes. Okay, I could have just made them dots, but I wanted to make the holes stand out, and so you can see that sometimes we have to grow the heap because we can't find a hole big enough, and other times an object will go into a hole. Oops, so you can see holes being created and objects going into the hole, and eventually we're going to run out of memory because we're going to fill up the heap, and there aren't any holes big enough to hold any new objects. Oh, there we go. And program finishes, and you can see that we were pretty efficient here. 97% of memory was used, and only about 3% was left as holes. And you can see the requests and number of allocation requests, deallocation requests, and so forth. Okay. Anyway, I thought you might be amused to see a simulation of, if you imagine this being the heap, and these A, B's, and C's are objects that are being allocated out in the heap, and the various holes that are created when objects are being deallocated, and you saw some of the holes being reused by new objects. Okay. Anyway, so that's what a memory manager has to do, or specifically a heap manager has to do, is keep track of which blocks are allocated, where the holes are, and their sizes, and so that when a request comes in the first fit algorithm, we just scan and look for a hole that's big enough. The first hole that's big enough. Now, so even if the object that we want requires 2 blocks, and the first hole that we encounter is 20 blocks, we're going to put the object in that big hole, and of course then that leaves 18 blocks left over as a new hole. Okay. All right, so that's what it means to have a memory manager managing your heap. Okay. All right, any questions about that? Okay. As I said, this was actually an assignment in my operating systems class. Okay, so I'm going to kill all this, get rid of Control C here, go away. Control C here, go away, and finally Control C again. All right. Okay, so then exactly how are we going to manage the heap? Okay, so now you have different ways of allocating memory for blocks. Okay. Now, the other question is, should you periodically compact the heap? Okay, so you after a while, your heap looks like Swiss cheese, and you've got holes everywhere, and that means that when it comes time to allocating a new block, you have to go searching. When it comes time to allocate a new object, you have to go searching looking for a hole, okay? So a possible thing that you can do is periodically compact the heap by moving all the objects, against one end of the heap, so that gets rid of all the holes, and then any new objects would just be appended at the end. Well, after you've compacted, you're going to end up with a big hole at the other end of the heap, and so new objects can just go in there, and then there'll be fewer holes to search, okay? Now, the problem with compaction is that, well, you have these objects allocated out in the heap. Presumably, you have pointers to those objects, okay? And so if you compact the heap, which ends up moving an object, well, then you have to update that pointer, okay? And so if you're going to do compaction, then you have to keep track of where all the pointers are. Okay? So if you move an object, then you'll find all the pointers to that object, and then you have to update the pointers because you moved the object. Okay? So compaction does have its disadvantages. Okay. All right. Garbage collection. Okay. So when an object is no longer being used, and quite often that means there are no longer any pointers to that object, then that object is garbage, okay? Now, as I said, in languages like C and C++, before an object becomes garbage, you want to explicitly deallocate it by calling delete or malloc on it, okay? And, otherwise, if you don't, and the pointer variable that's pointing at that object gets set to point to something else, then the object that it was pointing to no longer is accessible, and therefore it just sits there in memory, hogging up space, okay? And that's the garbage, okay? So then how does automatic garbage collection work, okay? And so, well, first of all, the whole idea of automatic garbage collection of the heap, while your program is running, was invented by a computer scientist named John McCarthy back in 1959. So this is not a new concept, okay? He had invented a language called Lisp, and it required runtime memory management. So he came up with the idea of automatic garbage collection. So we're going to look at various algorithms for doing garbage collection. Okay, and okay, there are. We'll look at 4 of them: reference counting, mark and sweep, stop and copy, and generational. Okay, so these are the algorithms for clearing the heap of garbage. Okay? All right. Now, the whole idea of automatic garbage collection is great for programmers, right? As I said, in Java, you call new to allocate new objects, but then when you no longer need that object, and perhaps the pointer that was pointing to it is pointing at something else, and there are no longer any pointers pointing at that object, the garbage collector comes in and automatically gets rid of that object, okay? And so that's wonderful. That means that that's one less thing a programmer has to worry about, okay? However, that comes at a cost, okay? Automatic garbage collection comes at a cost, because that means that when your program is running, okay, the garbage collector can decide, oh, I need to start collecting garbage, okay? And so it jumps in. Now, of course, while it's doing that, your program can't continue running because the heap is being modified, and so your program gets paused while the garbage collector comes in and cleans up the garbage, and then your program can resume. Now, if this is a real-time mission-critical real-time application, you shouldn't want that happening, because you're processing signals that are coming in real time, and all of a sudden the garbage collector says, hey, I want to go in there and do some cleanup, and suspends your program, and you end up missing some signals. Okay, so automatic garbage collection can be a detriment. Okay, and so even languages like Java, which does have automatic garbage collection, um, allows you to turn it off. So if you know your program is in this really critical phase and is monitoring things in real time, you can tell the garbage collector, hey, hands off until I say it's okay again. Okay. All right, reference counting. Okay, so how would a garbage collector that uses reference counting work? Okay, so here, whenever you allocate um, memory, okay, there is a little bit of extra room left over for a reference count. Okay, so you know, maybe your object is 100 bytes, and what really gets allocated is 104 bytes because you need those 4 bytes for a reference count. Okay, now every time you have a pointer point at that object in the heap, you increment the count. So presumably when you first create the object in the heap, it would have a count of 1 because when you create the object, you're going to set a pointer to it. And later on, other variables may end up pointing at that object. So each time that happens, you increment the reference count. Okay. Now, whenever an object that was pointing at, whenever a pointer that was pointing at the object no longer points to it, maybe that pointer got set to null or it got set to point to another object, then the reference count is decremented. Okay. Now, when the reference count becomes at 0, that means nobody is pointing at this object, and therefore it becomes garbage, and the garbage collector can then deallocate it. Okay. So the memory manager has to keep track of all the objects that have been allocated so they can monitor the reference counts. And as soon as an object's reference count becomes a 0, that means nobody's pointing at it, is inaccessible from the program. Therefore, it can then denote that to be garbage and deallocate the object, okay? Which then, of course, opens up a hole in the heap. Okay. Now, this mainly works until you have cyclic graphs. Okay, and here's an example of it. Okay? We've got 3 objects in the heap. Okay, so I'm showing 3 objects, and there's some data structure, and each object points to another object, and so you have a cyclic graph here. Okay, and therefore the reference count will never become 0 for any of these 3 objects. Okay, and it looks like you cannot access because there's no pointer from the program to any of these objects. And so now you've got 3 objects that are pointing to each other in the heap, and they're inaccessible. And so you have garbage that cannot be cleaned up. Okay? You would hope that if you're using reference counting, that you never actually create a data structure like this. But if you do, then you're going to end up with garbage that the garbage collector cannot find. Okay. Turns out that I mentioned earlier that C++ now has these smart pointers. Okay, smart pointers use reference counts. Okay, and so smart pointers will have problems when you create this situation. Okay, so hopefully you won't. Okay. All right, so that's garbage collection using reference counts. As soon as the heap manager sees that an object's reference count has gone down to 0, it then can automatically deallocate that object. Okay. Now, another algorithm is called mark and sweep. Okay, and it basically keeps track of which objects are reachable by a chain of references from pointers within a stack frames. So in a stack frame, then you have values of local current runtime values of local variables, and some of those variables could be pointers. They will be pointing at some object, and so you can imagine the garbage collection algorithm following these pointers. Maybe the pointer points to something which in turn points to something else, and so forth. And so periodically, it's going to look at all these pointers that are coming out of the stack frame and following all the pointers, until you finally get to a null pointer, and marking all the objects along the way, okay? And then after it's made that sweep, okay, marking all the objects that it was able to reach, then it does, the first pass is called marking, okay? So it's going through marking all the objects that it encounters by following all the pointers. And then the second phase, the sweep, okay, is going to go through, and all the objects that were not marked then are garbage. And during that sweep phase, it will deallocate those pointers. It will deallocate those objects, okay? So that's called mark and sweep, okay? And that relies on basically starting with variables in the local variables array in the stack frame that are pointer variables, and following all the chain of pointers from each of those variables, and marking the objects that it encounters. And so then the unmarked objects must be garbage, and they can be swept by deallocating them, okay? All right, that's mark and sweep, okay? Okay, here's one that's called stop and copy. Okay, well, it's a very descriptive name. That's what happens at runtime, okay? So here, the heap is partitioned into two halves, okay? And at any one time during runtime, you're only using one half the heap, because that means whenever you're allocating a new object, it's only going into one half the heap, okay? Now, sooner or later, that one half of the heap is going to fill up, okay? You're not going to be able to find a hole big enough to fit an object that you want to allocate. And so at that point, you stop, okay? Your program stops, and then the heap manager copies all the objects from one half the heap to the other half. Remember, you only use one half the heap at a time, okay? So when it does that copying, it's also compacting it. So that when it's copying the objects from one half to the other half, it's making sure that the target half is compacted, okay? So then, of course, we have all the issues of updating pointers and so forth, okay? Now, after we've copied from one half of the heap to the other half, then this other half becomes the active half. And when the program restarts, that means that any new allocation will be going into this other half the heap, and the original half can then be cleaned out, okay? And so you keep switching back and forth between this half the heap and the other half the heap, okay? And a switch involves stopping the program and copying the objects from one half of the heap to the other, okay? That's called stop and copy, okay? And you can imagine how disruptive that can be to your program's execution. It's chugging along, and all of a sudden everything stops, and forever, and then for however long it takes for the heap manager to copy everything over from one half the heap to the other, that's how long your program is going to be suspended. So, if you've allocated a very large heap and you've created lots and lots and lots of objects out there, maybe they're all pretty small, then you can imagine how long this copying operation might take. Okay? Because not only does it have to do the copying, but it has to update all the pointers. Okay. Okay, so just like with mark and sweep, we have to keep track of where all the pointers are so that we can update them. Okay. All right, now generational garbage collection. When I was working at IBM Research, IBM was actually one of the pioneers in using Java. Shortly after Sun invented Java, there were more Java programmers at IBM than there were at Sun. And so because Java had automatic garbage collection, IBM came up with this very clever algorithm. There's some theory behind it. And I had the opportunity when I was at IBM Research to play around with this algorithm. Okay, so here's the idea that most objects that you create in a program are short-lived, right? Your program's executing, and you create an object, and it lasts for a little while, and then you don't use that object anymore. Okay. Now the long-lived objects, okay, the ones that are not short-lived, well, they tend to last until the program terminates. Okay, so either you have short-lived objects or you have long-lived objects that once they've been created will stay around to the end of the program. Okay, that's the theory. Okay, so you would then partition the heap into a new generation area and an old generation area. Okay, and here's how that works. Okay, when you allocate a new object, it goes into the new generation area. In other words, when you call new to create an object, the heap manager will then put that object in the new generation area. Okay, and the heap manager keeps track of how long an object lives. How long has it been since the object was created, and once the object has lived past some predetermined threshold of time, that object gets moved from the new generation area into the old generation area. Okay, so your program creates an object. Okay, now that object goes into the new generation area, and if this theory is correct, most objects are short-lived, and so the object is allocated in the new generation area, and then a short while later, that object is deallocated. Okay, but there are some objects that may live a long time, and if an object that has been allocated in the new generation has lived past a certain predetermined amount of time, the heap manager says, okay, this is a long-lived object, and it moves it into the old generation area. Okay. Now, of course, as it's moving from the new generation area to the old generation area, just like stop and copy, the new generation area will be nice and compacted, right? Because it's moving objects into it, and so it's going to keep it compacted. Okay. All right. So because the objects in the old generation area are, by definition, long-lived, that area is going to stay pretty compacted, right? You're not going to be making too many holes in there because those are long-lived objects, okay? And the new generation area, well, because by definition, those objects are short-lived, they come and then they go, they come and then they go, you're not going to end up with a lot of Swiss cheese, right? The objects are going to be deallocated, and you're going to have a lot of big holes as opposed to lots of little holes. Okay, and so in that case, then you shouldn't need a lot of compacting of the new generation area because you're going to have lots of big holes in there. Okay? So that's the idea behind generational garbage collection. You set some kind of threshold that says if an object in the new generation area has lived beyond this threshold of time, then it gets moved into the old generation area. Okay. And then by separating the new objects that are short-lived from the objects that are long-lived, then by managing them in these two different partitions, it turns out that neither partition is going to need a lot of compacting. Now, what is this predetermined threshold? Okay, now presumably that's something that maybe the system administrator can set. Yeah. Now, how does he know what to set it to? Is it 5 seconds? Is it 5 minutes? Okay. Well, in a production shop, you tend to run the same programs over and over and over again. And if you instrument the program to monitor, how long objects live after they've been created, maybe you have a special debugging version of your program where you put a little timestamp or something for each object that's allocated out in the heap, then after a while, you can kind of come up with a good threshold for when a new generation object becomes an old generation object. Okay? In a production shop, you tend to run the same programs over and over again. And so there you're able to come up with this threshold. Okay? All right, that's generational garbage collection. Okay. Now, there is an argument. Well, first of all, any questions about these algorithms? And there are more, believe me, but these 4 tend to be the most common. Okay. Now, should we aggressively manage the heap? Okay. I mean, how if you have a heap manager, how aggressive should it be? Okay, so aggressive heap management means you do a lot of garbage collection, yeah, even when it's not necessary, right? A garbage collection really becomes important if it becomes harder and harder and harder to find a hole to put a new object in. Okay, and so after a while you say, okay, I got to go in there and collect all the garbage to make more holes. Okay. Now, aggressive heap management says you go in there and do garbage collection whether or not it's really needed. You just do a lot of it. Okay. And the idea there is that, hey, we want to make it as easy as possible to find a hole whenever we want to allocate a new object. And by doing lots of garbage collection, you're going to guarantee that there are a lot of holes and even some bigger holes out there because you've been very aggressive. Okay. Now, one reason to have aggressive heap management is that you want to keep that heap as small as possible, right? You don't want the heap to be growing. And so by aggressively doing garbage collection, you're going to make sure that there are enough holes for new allocations so you don't have to keep growing that heap, okay? And keeping the heap as small as possible is a big performance boost because of what's known as reference locality. Okay? Studies have been done where they monitor a program's references to memory, and the references tend to cluster. Okay, so here's a cluster of lots of memory accesses or updates or whatever in this region of memory, and then here's another cluster maybe later on where a lot of accesses in a fairly narrow, fairly constrained part of memory. Okay, and so by keeping the heap small, then you're improving this reference locality. Okay, because if the heap grows too big, then the operating system's memory manager may decide that, oh, we need to page some of the objects out to a backing store. So that's the whole concept of virtual memory, in that virtual memory can be larger than the actual physical memory, because part of the virtual memory has actually been written out to what's known as a swapping disk. Okay. Now, disk I/O is very, very slow compared to memory, main memory. Okay. And so you want to make sure that by keeping your heap as small as possible, that none of it actually ends up being paged out to disk. Because you only have a certain size region of memory to work in, and so you want to keep that heap as small as possible. Okay. All right. So aggressive heap management is important does have its important advantages. Okay. Now, the trade-off then, of course, is that for the garbage collector to jump in and start cleaning up, that could disrupt your program. Your program may have to be blocked. You know, the program you wrote that's using the heap may end up being slowed down or temporarily blocked while the garbage collector is out there doing its thing. And so if you have very aggressive garbage collection, your program is going to see a lot of these interruptions. Okay, but you know, it is true that paging to disk is very, very, very slow compared to all the other operations that your computer is doing. Doing disk I/O is very, very slow. And so you may have to have a balance between aggressive heap management to keep that heap as small as possible so that it doesn't get paged out to disk, or having so many, by having such aggressive garbage collection, you're interrupting your program too much. Okay. So as a system operator, and a compiler writer, these are the sorts of things that you have to consider. Okay. Now, I mentioned there are some algorithms. Believe it or not, people are still trying to come up with good algorithms for managing the heap, and so there's still opportunities for research. You know, if I don't know, you're looking for a senior project or something like that, here's an idea. You know, come up with a brand new garbage collection algorithm, and maybe you can become famous. Okay. Now, I have an idea. Now, I have not pursued it, but let's say that you're in some sort of shop, and you know, an IT shop, and this shop tends to run the same programs over and over and over again. You know, maybe it's payroll or whatever. Okay, your bank, and sure, every night you tend to run a set of programs, and using machine learning, you can train the machine learning algorithm by using all these runs as sample data to train a machine learning algorithm to come up with some sort of adaptive garbage collection that uses the appropriate algorithm for a given mix of applications. Okay, and so hey, if you decide to do research in this area and you end up with a paper and you become famous, then remember the name of your professor who suggested this to you. Okay. All right. I actually have a whole textbook, which, you know, back in the old days when we met in a classroom, I would bring and show the students. It's like a 1-inch thick book that has all these various algorithms. And so this is a big topic. Okay. So if you go into researching garbage collection, you can tell mom and dad that they are paying all this tuition so that you can become a garbage collector. All right, that's all I have for today. Um, uh, I'm trying to give you more time. You know, again, back when we were meeting in the classroom, I would say, okay, now you have 20 minutes of lab time where you get together with your team and I'll be around to answer questions. Well, here we are in Zoomy land. If you have any questions, feel free to ask. Okay, and if you're having any problems with Antler, hopefully you've gotten past most of them by now. If you have any questions about how to create a grammar, here's a common problem. You have some language that you want to compile, you write the grammar for it, and somehow the parser that Antler generates for the grammar isn't working. It maybe doesn't recognize some of the statements in your language. I mean, it thinks there's syntax errors, or it doesn't build the right tree, because you're looking at the parse tree that it builds. Now you write a sample program in your language, and the Antler generated parser doesn't do the right thing. So that could be an issue. Okay. So there are a number of common problems that students have run into that definitely put it on the discussion forum, and hopefully other students will come up with ideas or I will answer. Okay. All right. Any questions? Okay. Before I let you go, I do want to point out that I think it was Saturday, I put out an announcement about this internship at NASA Ames. And I am the PI for a multi-year, multi-million-dollar grant that I managed to get from my former colleagues at NASA. And this is to pay for student interns. Now, right now, Ames is still locked down because of the pandemic. So in the past year, I've only managed to hire 4 interns, and we're in the process of hiring a 5th one. When I did this 2 or 3 summers ago with a much smaller grant, I had like a dozen interns during that summer. And I hope that when the lockdown at Ames is over, again, I will have a small army of student interns, okay? But because of the lockdown, there have not been that many internships, okay? Currently, there are 2 of them, okay? The one that I announced on Saturday just opened, and if you are at all into natural language processing, okay, this is for a recommender system. And you know that when you buy a book on Amazon, it immediately gives you some suggestions for other books you might want to buy. And that's because of their recommender system. They've collected data on all the past purchases, and they see what books tend to get purchased together. And so they're making that recommendation to you. And that's all done with machine learning and clustering algorithms and so forth. Okay. Now here, this is a recommendation system for publications. So of course, NASA has all kinds of scientific papers. And if you're reading a paper, let's say you log onto their documentation library and you select a document to read, what NASA wants is for the system to recommend other papers that discuss the same topic, okay? Because you're doing some research and you want to read about a particular rocket. Well, you found one paper on that rocket, then maybe there are other papers that talk about that same rocket. Okay, that's the recommender system. Okay, so this is done in Python. Okay, which is very common programming language for doing machine learning and AI. And they're looking for somebody who has some background in natural language processing. The papers presumably are all written in English. There's this algorithm that's very commonly used to when building these recommender systems. So they're hoping that somebody would be familiar with that algorithm. Okay, I've already gotten resumes from about 4 students who said they know this algorithm. Okay, and hey, if you've done any work in the past with a recommendation system, recommender system, then these are the qualifications for this particular internship. If you meet these qualifications and you're interested in working at NASA Ames, okay, hopefully before the end of the summer, you'll be able to work on campus, okay. I can tell you as a former senior scientist at NASA Ames that it is a really fantastic place to work. Okay? It's like being on the college campus of, say, MIT, where every building is doing some cool research. And so, let's see, for undergrad, if I remember properly, we're paying around $23 an hour. So it's definitely above minimum wage. And if you're a grad student working on your master's, I think it goes up to around $28 an hour. But I think most of you are undergrads. Okay? So this is the position that just opened up, and I'm starting to get resumes. Now, there was a previous position that I announced a while back. This one involves a GIS. Whoops, sorry. What did I click? Click the wrong thing. Okay, this one involves GIS. So if you have any experience with geographic information systems, okay, and you program in any of these languages, C, C++, Python, and you know something about databases and SQL programming, then this is the internship for you to apply to, okay? Surprisingly, this has been out for a couple of weeks. I announced this a couple of weeks ago, and I have not gotten a single resume. So I find it hard to believe that there's no student at San Jose State who knows GIS, databases, and can program. And so I have not gotten any resumes, which means that that position will probably be taken by a student from some other university. And I really, really want somebody from San Jose State to get this position. So, so we currently have 2 openings. Okay. Any questions about these? Okay. Gotten some chat messages. Prem, yes. I have forwarded your resume to the hiring manager. So now it's up to the hiring manager to decide. I did point out that you do have familiarity with LDA, which is not too many undergrads have that experience. Okay. All right. Any questions about NASA or compilers, whatnot? Isn't it cool that they've flown that helicopter 3 times already? And, boy, it makes me wish I were still at NASA, since I was very much involved with 2 previous rovers, so I can see what I'm missing. And this one's got a helicopter. Isn't that cool? The idea is that if this one helicopter works out, they may, in a future mission, send a swarm of helicopters buzzing all over Mars. And they're thinking about, hey, how about a helicopter buzzing around Titan, one of Saturn's moons? Now, I remember a while back, NASA did land a lander on Titan, and they took pictures of all the lakes and rivers. Of course, they were lakes and rivers of methane, but so we have been to Titan, and it has a very thick atmosphere, and so they can fly a helicopter there. The atmosphere on Mars is very thin. The air pressure is only 1% of Earth, and so that helicopter has to have big rotors and has to spin very fast. And but they've successfully flown it 3 times already. Okay. So cool stuff going on at NASA. Okay. All right, I blathered on long enough. Any questions? If not, then I will have my office hour at 4:30. So you're free to come by and chat. Okay. All right, so if there are no questions, I'm going to shut down. Okay. And see you all on Thursday when we'll cover another topic that's of interest to compiler writers. Okay. All right, thank you for coming.